So I have seen problems similar to 18 on old AP tests. Okay? So this is a thing you should know how to do, or at least the trick that I'm going to show you here at the beginning of it. Okay? So it says, with what speed would Roy pass through the center of the Earth if falling through a tunnel through the center? So the idea is, you've got the Earth, and somebody has taken the time to dig a tunnel all the way through the center. All right? And so Roy is going to fall through the center, right? Clear? All right. So the problem is, at the surface, like right now when he first steps into the hole, what's his acceleration initially? 9.8, right? Is it constant? No. What would his acceleration... Suppose a squirrel just magically appeared here at the center. Here's a little squirrel at the center of the Earth. All right, assuming that, he didn't melt because of, the core being very, very hot. What would the squirrel do if he just, appeared there? He'd just hover there, right? Why?
Because there's equal mass on both sides.
Is equal force on all sides, right? Kind of the shell theorem, right? He's at the center of a shell, right? Does that make sense? He's being pulled up with just as much force as is being pulled down, right? Good? All right? So the idea is here the acceleration is 9.8, here the acceleration is 0. What would happen over here? Be 9.8 the other way, right? So what do you think, not even in terms of numbers, but what's Roy going to do once he steps off of that thing?
He's going to fall.
Well, yes, he's going to fall. Yes. So his acceleration starts out 9.8 down, so he's going to speed up, speed up, speed up. What's his acceleration at the middle? 0. So he speeds up all the way to the middle. Then what? Then he slows down, slows down, slows down, slows down. Stops and bounces back up, right? So somebody said he's going to bounce. It's going to look very similar to this thing almost killing me. What did I do with it? I just pulled out some springs right here. So it should, I think, look very similar to him doing this. Cool? All right, so let's see if we can figure out kind of what's going on. So the problem is that the net force on him is changing, right? So let's think about what would happen when he's right here arbitrarily. Okay? So I'm going to label two distances. Let's call the radius of the Earth capital R. And let's call this distance the distance he is from the center of the Earth at that point. We could call it lowercase r, which would be totally fine. But to make a point, I'm going to use x. Is that okay? And if that's going to weird you out, use lowercase r. It doesn't matter. Okay? So, in the video, what we learned was that if you are inside a solid sphere, that your force of gravity at that point is equal to g times your mass times the Earth's mass divided by r squared times, you guys remember? R over r, or for us, x over r, right? In other words, it's equal to the force of gravity at the surface times the ratio of, your radius to the overall radius. Follow? All right. So, good? Do you guys agree that this is a constant? Right? The Earth, your mass is the same, the Earth's mass is always the same, the radius of the Earth is always the same. Yes? Let's call that something. I don't want to keep writing that bullshit over and over again. Let's call it K.
KX is pretty. Whoa!
Oh, a lot of you guys are saying oh. Why are we saying oh?
It's a spring.
It's a spring. It's literally the exact same as this. With this as my spring constant. Cool? All right? So, all right, great. So, that's neat. That's a cool thing. How do I then use that to figure out the velocity when we get to the center? There are easy ways to do it, and there are hard ways to do it, and one really easy way to do it. Thoughts?
Well, force is 0.
Well, that's your instantaneous force, though, right?
You see.
When you say integralize it, what do you mean? So there is an integral you can take that will work.
That's what I'm saying.
Oh,
Because then you get the other one, like the 1/2 K.
Oh yeah, 1/2 kx squared. What does 1/2 kx squared represent? Elastic potential energy, or for us, gravitational potential energy at any given point, right? Follow? So, what should be true? Up here, my u is 1/2 k times r squared, right? What's my kinetic energy there? Okay. Then, when he gets to the center, now what's my elastic potential energy? 0. Oh, that means that my kinetic energy must be 1/2 k r squared again. Follow? So to solve this thing, did I do that too quick? Are we good? So to solve this, all I'm going to do is I'm going to go 1/2 k x squared. Oh no, sorry, 1/2 k r squared equals 1/2 mv squared, and solve it. So the trick though is I didn't give you the mass. So let's see, the 1/2s cancel out, and I know the radius of the Earth. What was k though? Unfortunately I just erased it. Do you guys remember what k was?
G, M, M.
It was g m over r cubed, I think, times r squared equals mv squared. Oh, my m's cancel. A whole bunch of my r's cancel. And then solve it.
Yeah.
What? Did I do something wrong?
No, I just
That's half the acceleration of gravity.
Gm r squared.
Yeah, no, but this is 1/2 of the exit velocity stuff, or escape velocity, right?
Root 2, because the 2's in the square root.
Yeah, v is equal to the square root of, and what would be 2gm over r, and now it's just gm.
Oh, right. Oh, for v squared. I got you. Yes.
Yeah.
Agreed. Agreed.
Is there any like significance of that, or no?
No, not really.
Is it significant that it's the same?
Yeah.
So, we had X earlier. Is there a reason that we switched it to, like, I'm confused. How did we just kind of like.
Oh, so the x showed us, shoot, I wish I hadn't erased that before. The reason I used x is I wanted to end up with f equals kx.
Oh, so you
Just because you've seen Hooke's law. All right. Now, I didn't switch it back. I switched it back to capital R.
Yeah.
Why?
Oh, because that's like the starting.
Because at the starting point, here x is equal to r,
Yeah.
capital R. Good? All right, so this is a common trick. Anytime you have a hole through the center of the Earth, remember that it's going to end up being a spring problem. And to illustrate it, to prove it, you need to do this trick where you write your force of gravity like that. Okay? And then replace all of this with a k, some constant k. Cool? All right, so let me say this. So yeah, you're right. So me saying that it was easy is misleading. When I say it was easy, I meant like mathematically it was fairly easy. It was algebra, right? Coming up with the idea, absolutely not easy, right? Okay, so that's a trick you should make a note of. Okay? The hard way to do it would be to try to integrate. Like you could, I guess you could divide this by mass and then try to integrate the, if you divide by mass, that gives you acceleration, and then try to do an integral. But that gets ugly because your integral would be with respect to time, so you'd have to find a way to put time in there. It gets ugly. There are ways to do it, but it's ugly. What mass would you divide by? If you're trying to find the acceleration, would you divide by the mass of the Earth or the mass of the little m, right? No, that's okay. Good. Important.
Does the X over R come from the shell theorem where it's like
Yeah.
where it's like think of the Earth as like instead of thinking of like the shell, you think of it as like infinite.
Yeah, basically. So, I mean, if you really want, at some point, I'm happy to sit down and show you where it comes from. So the idea is, what you need to do is you calculate the mass of everything inside the shell and find the force of gravity by that. And then everything outside of the thing, is zero. And it actually, it's all algebra, but it's a lot of algebra where you need to look at the density of the Earth, the volume of the sphere, you know what I mean?
Yeah.
So it gets a little bit ugly, but.
But it just turns out to be something.
And it just turns out to be that, exactly. Adam.
This question has basically remotely nothing concerning the homework, but so you know how when people, like when kids ask you like why we can't feel the Earth spinning, and you say because like it's spinning so slowly that we can't feel it. Could you just say because you're going the same speed that the Earth is?
That's actually the answer I usually give.
Yeah, and
It's
then
like being in a train, right?
and if it were hypothetically like spinning faster, would like the air and atmosphere go with it, or would there be like a windstorm all the time?
I believe that it would go with it because eventually the friction, I think, would speed the air up to the rate. I don't think, I mean, if it suddenly, like if the Earth suddenly started spinning faster and faster, for a little while we'd be screwed. But eventually everything would normalize out. Is my, I don't know that, I've never thought about that before, but that's my knee-jerk reaction to that. Yeah.
I have a question related to that question. You know the Nike commercial where the Earth stops and they all go out and run to make it go fast again?
I believe I've seen
Then
that.
they go the wrong way, so they run the other way. How many people would that actually take to cause that sort of acceleration? You only need the antithetical pole.
One and a lot of time.
With the acceleration,
Right? Because,
about 2 seconds to speed it up from the opposite of the Earth's.
say that again?
It took about 2 seconds in the commercial.
Oh, in the commercial. Oh, I got
Speed
you.
it
Yeah,
up
figure it
from
out. It's a torque equals I alpha problem.
speed
Figure it out.
to the
Torque equals I alpha. Figure it out. You can do this.